So in the first argument, one can say, okay, the total effort will be the same. But if you ask actors, they say, okay, if I remember my lines, I also remember the other one's lines. So at the end of the studying, both actors know everything. So this suggests that the effort for studying the script by two actors is almost double. Okay, so let's look to information theory. What does information theory says about this problem? We start with Shannon entropy. So there is this nice additivity of information. If we have two variables, information in one variable, information in both variables equals information in one variable plus the other. We also have the same relation when there is a condition, Z. So that means we can split up in many places by induction and see that the total studying effort, if we measure our studying effort by Shannon entropy of our variable, somehow suggests that in both settings the total effort is the same. Now the question is, what happens with Kolmogorov complexity? So for those people who don't know it yet, I just say it's another measure of information, but it does not depend on a probability distribution. It measures the information in a bit string in an absolute sense. And for Kolmogorov complexity, we also have some law of symmetry of information. It's stated here. It's called symmetry of information. It's invented by some Russians. And but the problem is there's not perfect symmetry of information. There is a small error term. That means we cannot use symmetry of information to break up in many pieces. So there is a small difference. There is a conditional version. This difference is still there. And now when we break up in many pieces and we collect all complexity terms which correspond to one actor and all the terms for another one, we don't have a nice composition. Each time we split up by induction, we have constant error, right? So that means if we split up in two n pieces, we have linear error, and this linear error can be larger than the complexity. So the complexity is bounded by the length of the string. Complexity of bit string is bounded by its length. So we have a decomposition where the error is bigger than the length. So we need first other definitions. I will give you in a minute. And secondly, we can again check whether our equality holds or not, and wonder which setting will be followed. Will there be symmetry of information or not? So let us do a small tutorial. What is Kolmogorov complexity? So it is theoretically possible that contributions of both actors will be bigger with this notion of information. So now I explain you what is Kolmogorov complexity. So it measures the information in a bit string. Here you see 3 bit strings. On the top, you have a random one. So it's from some website about random noise from atmospheric pressure and blah, blah, blah. So it's believed to be perfectly random. And one can say this string cannot be compressed. You cannot write a small program that prints this string. The program has to store all the information. The second string is a bit string that only contains zeros. This is highly structured, right? So it is somehow a small program can print this string. So this is a non-random string. The second one is also structured, so it's just a list of all strings. This one you can compute, but the frequencies are always nice. So all limit frequencies are 1/2, even if you look to pairs of bits and so on. So this measure, Kolmogorov complexity is designed to capture all possible structures, but structure, it means if a string is highly compressible, it measures somehow how much information can be stored in a smallest possible space, but still computably decompressible. So here is the definition. It starts from a Turing machine, which is a mathematical notion of a computer, and the complexity of a string relative to a machine U is given by the smallest length, the minimal length of a program that prints the string. So a Turing machine is called optimal if it assigns the minimal measure of information to a string, right? So please, if there is problems, tell me now. I see that many of you are very tired, but don't worry. Yeah, it's all this traveling and other talks. So please interrupt and ask questions. There is, as I told you, there is no reason to do all of the presentation. I only want you that you remember something interesting. So all work is published now, but it seems that it's not very, not many people care. So I came here to talk about it because I think it's very interesting. This causality problem is something interesting, but I do it for you, not for me. That's what I wanted to say. Okay. So optimal Turing machines exist, and if we have two of them, so that minimize complexity up to a constant, then we have a notion that is independent from the machine that we choose. So if we have two optimal machines, so two machines that minimize the measure by a constant, then they give the same information curve for strings up to a constant. So we will focus on asymptotic results. As soon as there is plus O of 1 in our equation, it's machine invariant. So now I list you some direct properties. So the first we will need, the others we don't need, but it's kind of small exercise. There are people who say that every talk should have at least a small proof, so that we will do very small proofs just to get used to the, to the notion of complexity. First, result says that complexity is bounded by the length of the string. So why is this? We can have a very simple compressor that just, when it receives a string, just go to the halt state. So the input equals the output. For this trivial compressor, any string is a program for itself. So on this simple machine, complexity is bound by the length of the string. Is this clear? Yes? Now, complexity is defined by an optimal machine. That means changing the machine will at most increase the complexity by a constant. So for any machine, we have O of 1 plus a constant. There exist strings with very small complexity, like in the second example. To print n zeros, we just have to store this number n. We can store it in binary, so it will take log n space to store it. Right? So we can define the complexity of numbers just by this relation. Then most strings are random. I will not explain you the proof to save some time. But so most strings of length, some length n, that means a fraction 2 to the minus c of strings of length n, are random. This means have bigger complexity than n minus c. And then there is a small result. If f is a computable function, then the complexity of f of x is smaller than c of x, because the short program for the output f of x is just given by a short program for x, and then after this program is evaluated, one can compute a function f. So this works for all strings x, so we get this relation. So the size of the so the complexity of the function does not depend on x. So we have complexity of f of x is at most c of x plus O of 1. Now I see some people looking strange. So what's the problem here? So when you have a short program for x, then you can add to this program a program for f, and then you have together a program for f of x. First you evaluate short program for x, and then this program evaluates this result, which is x, and you get f of x. This you can do for all x. So here we have some bound. O of 1 here depends on f, but does not depend on x. Then there is this property that complexity is not computable. And this is a funny story. This is very, very paradox, is the reason. So the Berry paradox says the following. So consider the following number. The smallest number that has no description in less than 20 words. So this number has by definition no description in less than 20 words, but I just give you one with 12 words. So this is Berry paradox. So if this number is well defined, there is a big problem in mathematics. And the same reasoning we can apply using the rules we have before. So consider the following function, the function that maps n to the lexicographically first string x that has complexity bigger than n. Yes? So by definition, complexity of f of n is bigger than n. Now assume that that complexity is computable, right? Then f is computable, this function. We can just search for the string if we can evaluate this guy. Now we know for computable functions, complexity f of n is smaller than complexity of this number n. Here is the definition of complexity of a number, which is bounded by log of n, by this observation. So we have that complexity of f of n is smaller than log of n plus O of 1. O of 1 does not depend on n. So we have direct contradiction here. So this is the proof for the lecture. The proof says that complexity is not computable. And actually this is a quite important result when we consider symmetry of information. For there we need some variant definitions. So there is the notion of conditional complexity, which is related to conditional Shannon entropy. That means if you already know y, then it might be possible to give a short program for x. So this is the idea of conditional complexity. Now our decompressor has two arguments, a program and some data, right? Similar, we can have compressors that output two strings, a pair of strings. So this is basically the same definition as here. And again, we can have universal optimal machines and so on and so on. So this is the small tutorial. Oh, I need to state the property of symmetry of information again. So complexity of a pair equals the complexity of x plus complexity of y given x plus some small error term. And the reason of this error term has to do with non-computability of Kolmogorov complexity. There are actually several reasons, but many of them can be removed by changing the definitions a little bit. But there is, yes? Yes, this C is the same as here.
So what's the meaning?
That, what? Yeah, well, you cannot, it's difficult to improve to, it means that if you have some big complexity, say, whatever, 1 million or something, 1 million bytes, oh yeah, oh sorry, I missed the log. Yeah, thank you very much. Yeah, oh so yeah. Oh so yeah. So here should be a log, thank you. So the error is very small, it's only a logarithmic, but as you remember, we want to break up our equation, so there is still this problem, this creates a problem. And this problem is actually caused by computability theory. This term is there, cannot be removed because Kolmogorov complexity is computable, not computable. So it seems there is some fundamental problem. And this is the goal of the talk, to confirm that something strange happened when we switched from Shannon to Kolmogorov complexity. Yes? Yeah.
Not edited, that would create similar, and they're highly disputed. I mean, not that
Yeah.
theorists like it. They come up with physics, something like solid
Yeah, but I think conditional Salis entropy is kind of very controversial thing.
Very controversial.
Yeah.
It gives you the same flavor that you have an
Yeah.
extra term when you add these things up. Physicists are also, I don't know who is actually supporting it, but it created a lot of interest and a lot of controversy. And there are other measures that are not so controversial like Salis, but they have the same issue, that same property, that you don't have to assume additivity, so you can always get an extra term there. That could be a measure of complexity rather than just Kolmogorov complexity.
Yeah.
Sharma entropy or whatever, there were a lot of different entropies that go beyond the classical assumption of additivity.
Yeah, but Kolmogorov complexity, I think in itself is a very interesting measure, and there is kind of little controversy about this one. Yeah. Okay.
Some other entropy measures, because another entropy measure would give you the same kind of question you're trying to address.
Yeah. Yeah, I have studied this Salis entropy, but for me it's not interesting enough to write a paper about it or investigate. Yeah. Okay. Yeah. But please, if someone studies it, and to send me the paper after it, or the results or something. Okay. So this finished the tutorial on Kolmogorov complexity. So thank you for your mark, and let's now go to the next, the results. So I still need to tell you what's the online version of Kolmogorov complexity. So here is the previous slide again. So the breaking up is not possible. So let us assume some more some setting which is more closely related to the actors on the stage. So in the first setting, there were two big dialogues. Let's say the first 3 bits and the second 3 bits. If the first actor does the first part of the sentence of the script, and the second part, the second actor, the second part, then we can look to the smallest programs needed here and needed here, right? The first actor, this will be just Kolmogorov complexity of the first part. For the second actor, it will be conditional complexity. So this is a common communication tape. What appears here can be read by both actors, in particular the second one. So this is the setting when we split into 2 pieces, and we know that we have this nice additive formula. So the sum of minimal lengths of programs here and here equals complexity of the pair, so the minimal length of a program for one machine to print out X and Y. But what happens when we break in smaller pieces? Do we still have that the sum of length of these programs is equal to the complexity of the whole string? So let us first investigate some properties of online Kolmogorov complexity. So note that both problems can be optimized independently. So choosing this program does not depend on this program. It only depends on the dialogue that needs to be performed, right? So we can talk about odd complexity and even complexity. So now let us talk about odd complexity, because even complexity is basically the same thing. So again, we can say that there exists an optimal so this is the formal definition. Given each next bit, given a next even bit, produce the next odd bit for all bits. So here the properties, odd complexity is now at most half of the length of the string, because the program has to print only half of the bits. The odd complexity is also bounded by the complexity, because if you can print the full dialogue, you can print also only your lines of the dialogue. Now, if we add both equations, then we find some equation that measures the asymmetry of information, right? Sum of odd and even complexity of X minus this complexity is at most length of 2. And this is just the sum of these 2 equations, right? So here we find an upper bound for the asymmetry of information. We can find another upper bound if we sum this also for the even complexity. So then we find this inequality. And this inequality we get by the observation that if we know this program and this program, then we can recover the full dialogue. So now we have, the question is this inequality tied? And which of these one is tied? Or maybe they're none of them is tied. So this is the asymmetry. And this theorem says that asymmetry can be maximal. So it is possible that odd complexity is close to the full complexity, and even complexity is also close to the full complexity. So it's very easy to find a sequence for which only one of these relations hold. So the odd complexity is equal to the complexity of the full string if all even bits are zeros. The same for the even complex can also be maximal. But how can you make a string for which both are at the same time close to the maximal thing? Oops. There is something more. So recall this dialogue. When we merge the odd and the even bits, we can do it in one specific way, like this. Right? So one actor says a sentence, let's say this actor starts, and then this actor says the next sentence, and we can merge it like this. We can also merge it otherwise. Rather than this, we merge it like this. Right? We flip the order pairwise. And then this effect can disappear. And this is what this result says. X tilde is a different merging. And then additivity is restored. So this strange result says something about, yes? 5 minutes, okay, no problem. So this result says that, that there is some information about causality. And this I will explain you in a minute.
How is X tilde obtained here?
Sorry?
What is X tilde here again?
So first, odd and even bits. This you understand? And now we merge it in a different way. Yeah. Yeah, indeed. Yeah. So there's a very simple permutation, and this deletes the asymmetry of information.
Oh, so you're saying it's like, it's as if, so if you know the odd ones, you can actually predict the even ones.
Exactly. So the result is stronger. If you know the odd ones first, you can recall what the even one says.
But if you know the even ones first, then you can't.
Yeah.
But you construct one string system this holds, or does it hold for so many strings? Is it true for every string?
No, for one very special string. So, yeah. So I had to construct, and this was difficult construction. But for random string, there is no asymmetry of information. Because then the programs just give the odd complexity. The program for the odd complexity is just a program that says the random string. So if the script is in Chinese, then both actors, assuming the actors don't know Chinese, then they just have to learn by heart all their lines. And the hint of the other actor is no help. So then there is nice symmetry of information for random strings. Okay, so what happens with 3 actors? Same story. So with 3 actors, the total work needed is 3 times larger than the work for 1 actor, who learns the whole, not dialogue, trialogue, I don't know how it's called. Okay, but let's continue. So what about the upper bound? So recall one of the relations we derived was bounded by length over 2. So the theorem says that we can have even this asymmetry linear in the length. Then the question, can we have this 1/2? Can we have maximal asymmetry? And the answer is no. There exists some beta for which this is small. Now computing, so all the results I show you, there is no hope I can tell you the proof, even the intuition, because it requires very special techniques from the field, and then even some things I had to invent. So it was a difficult proof to find this beta, and the best value I found was 0.42, and this is 0.32. But I'm not sure, because it's 3 weeks of computation. It's very likely I made an error somewhere. So therefore, no paper, I just mentioned in the conference. Okay, so now the philosophic applications. I do have 3 minutes.
Yeah, like 2-3 minutes.
Thank you very much. Okay, so imagine there is some complex interacting system. For example, a brain, and you measure electric activity from 2 different areas. So you measure in regular intervals. So you get some measurements. But unfortunately, the timing of the intervals is not enough to see the communication, right? So the time resolution is not enough. You just get pairs, but you don't know whether X is a reply to Y or Y is a reply to X. So then we can use minimal description length argument. If we explain the story, first X, then Y, first then X2, then Y2, we can have a very large description, and when we flip it, so this is the same story of changing the order, yes, then suddenly the story becomes very short. So this is remarkable. So here is the theorem again, and the theorem says basically that the minimal description length of one explanation can be much shorter than the other explanation. So there is an interpretation in terms of causality. But I have to make some warnings, because strings are highly actually, so the generator, so this one special string for which this is possible, it's Turing complete. It can solve the halting problem. So I had to do some very special things to get the string. So this is kind of strange. Maybe it can point to a pathology of Kolmogorov complexity. Rather, it's not clear whether it means something. It can be very interesting or it can mean nothing. But when it says, okay, if results should be practical, so assume that results need to be practical, then we should look at polynomial time compressors and decompressors, right? But then everything is restored, even for one round of communication, because of one-way functions. So imagine on one hand we have 2 primes, and on the other hand we have their product, right? If we assume that factorization is hard, then the explanation that some unknown machine first generated the product and then factorized it into primes is very unlikely. But if we assume that the machine first generated the primes and then computed the product, this is likely. So these things also exist, using some complexity assumption for reasonable machines. So I will finish here. My talk touched, just one sentence, my talk touched the question whether causation implies correlation, and then there's a big question, is this a pathology of Kolmogorov complexity, or is this very interesting, and can this be inspire new algorithms to detect causality? I thank you very much for your attention. Good afternoon.